Hello students. Welcome to the session of Engineering Physics Laboratory. In this lecture we are going to discuss an experiment based on the magnetic field generated by current in circular coils. Magnetic fields are produced by macroscopic currents in wires. We will show you how to determine the variation of magnetic field along axis of current carrying coil. The aim or objective of this experiment is to study the variation of magnetic field with distance along the axis of a circular coil carrying current. In other words, to study the variation of magnetic field with distance along the axis of a current carrying circular coil and hence estimate the radius of the coil. The applications of this experiment is in various fields such as motors, transformers, microphones, compasses, telephone bell ringers, television focusing controls, advertising displays, magnetically levitated high-speed vehicles, memory stores, magnetic separators, etc. To study the variation of the magnetic field with distance along the axis of a circular coil carrying current, we need to have various components such as a circular coil, compass box, ammeter, rheostat, commutator, cell, key, connection wires, etc. A tangent galvanometer of the Stewart and G type. A tangent galvanometer is an early measuring instrument for small electric currents. It consists of a coil of insulated copper wire wound on a circular non-magnetic frame. Its working is based on the principle of the tangent law of magnetism. The purpose of the commutator is to allow the current to be reversed only in the coil while flowing in the same direction in the rest of the circuit. The rheostat is an electrical instrument used to control a current by varying the resistance. Another component is commutator. The purpose of the commutator is to allow the current to be reversed only in the coil while flowing in the same direction in the rest of the circuit. An ammeter is required to measure current value. An ammeter, from ampere meter, is a measuring instrument used to measure the current in a circuit. Electric currents are measured in amperes, hence the name. Instruments used to measure smaller currents, in the milliampere or microampere range, are designated as milliammeters or microammeters. The rest of the components are well known. If we pass a current of I ampere in the coil, keeping it vertical in magnetic NS direction and place the needle at a distance x from the center on any side of the arm, the magnetic field B acting on the needle due to the current in the coil is given by this formula, where n equals number of turns in the coil, A equals radius of the coil in cm, I equals current in the coil in amperes, x equals distance of the point from the center of the coil in cm. Here we are defining only formula. For detailed derivation and theory, you can check on our other videos. Let's move to the section titled Virtual Experiment. The link is given you. I recommend all of you to open link and perform the experiment with me, so that there is no confusion about how we perform the experiment. This slide shows the experiment setup for the virtual environment. We have already gone through the apparatus. Now, we will move forward and see how to perform the experiment in a virtual environment. Before starting the actual experiment, let us discuss Stewart and G type tangent galvanometer. The apparatus called Stewart and G tangent galvanometer is used to study the variation of magnetic field along the axis of current carrying circular coil and is shown in the figure. The tangent galvanometer works on the principle of tangent law. The magnetic needle is subjected to a magnetic field which is perpendicular to each other. One field is due to the horizontal component of the Earth's magnetic field, and the other is created by passing the current through the coil of the tangent galvanometer. Tangent galvanometer consists of a coil having a large number of turns and a small magnetic needle. The important part of tangent galvanometer is this magnetic needle. It is important to align the needle to magnetic meridian. The magnetic meridian is an equivalent imaginary line connecting the magnetic south and north poles and can be taken as the horizontal component of magnetic force lines along the surface of the Earth. Therefore, a compass needle will be parallel to the magnetic meridian. In this virtual setup, it is hard to match with the magnetic meridian. So, in this case we will rotate the compass box till the pointer ends read 0°-0° on the circular scale at zero current situation. This is known as initial alignment, which we are going to perform on virtual simulator. Let us try to align the compass. First, the preliminary adjustment should be made in order to make the apparatus in the magnetic meridian. First, preliminary adjustments should be made in order to align the apparatus with the Earth's magnetic field properly. The button initial adjustment is provided for this purpose. The experimental apparatus will be fully active only after the initial adjustments are made. On clicking the initial adjustment button, a zoomed view of the compass box will be displayed in the simulator. Two sliders rotate compass box and rotate apparatus are provided. Using the slider rotate compass box, the compass box can be rotated, and it is 90 to 90 reading parallel to the plane of the coil. Slight adjustments can be made, if necessary, with the left-right arrow keys. When the 90 to 90 alignment is exact, the slider rotate apparatus will be active. Using this, rotate the whole apparatus and make the aluminum pointer to read 0 to 0. Slight adjustments can be made with left-right arrow keys.
Now it is at 90-90, so once this is properly aligned at 90-90, this rotate apparatus will be activated. Now you can see it's not activated. It means this is not exactly at 1990, so I need to make certain changes. Okay, now it is okay. So with the help of rotate apparatus, I will align the needle at 00 degree, like this. Okay, so once it's done, it will show normal. We are again back to the normal view. So now, initial adjustments are done. Now we will go for the connections.
After the initial adjustment, it is time to make connections, as shown in the circuit diagram. This circuit diagram consists of a battery E, ammeter A, commutator, rheostat, and a key. You can see how they are arranged to make connections. Go through a video and make connections accordingly. You are not allowed to make a wrong connection, and you just need to connect the wires to on appropriate positions. It will get automatically connected. See videos and make connections.
So have a look at the circuit diagram. Battery is connected to ammeter, ammeter is connected to commutator, and the commutator is connected to the coil, and the other side of commutator is connected to rheostat. Rheostat's other side is connected to key, and the key is connected to the battery. So you will make the connections. Now you will see if you make some wrong connection, it will not be connected. Okay, so if it's not connected, it means you will understand you are making a wrong connection. So now other side of the ammeter is going to the commutator, connected here. This is going to the rheostat. It will be connected to the coil. Rheostat is connected to key, and key is connected to the battery. So our connections are done. So this is the key. We will click on insert key, and our circuit is complete. Now, before starting the experiment, we will set the initial parameters. Like this is your number of turns of the coil. Different values of number of turns are given. You can select any value. As we know that magnetic field is directly proportional to the number of turns of the coil. So more the number of turns in the coil, greater will be the amount of magnetic field. So you can select any value. Then this is your radius of the coil. Its minimum value is 5 cm and it can go up to 10 cm. You can select any value that you desire. And now this is your compass box position. So right now it is showing 0 cm because it is exactly below the circular coil. So this compass box position is what you will, what is your X, and this is adjust rheostat. Now you can see here the movement is there because of this. So with the help of this rheostat, you can adjust your current. You see when I'm moving this slider, here the ammeter, which reads the amount of current, is changing. So right now it is at 0.14, 0.09, like this, and here it is 1 ampere. So these parameters like number of turns of the coil and radius of the coil R and current I. These three parameters you will fix at the beginning and they will not be changed throughout the experiment. So in the experiment you will only change the position of compass box, that is X. So right now it is at 0. So I want to see now here because the current is flowing through the coil. So I have this perpendicular component of the magnetic field. Another component of magnetic field is Earth's horizontal component. So because of these two perpendicular magnetic field, there will be a deflection in the needle. So we need to see what is the angle theta. Click here, zoom compass box, and we can see here this is 66, and again this side is also 66. So this is your theta 1, this is your theta 2 for position X equal to 0. Now we will click on reverse current. So there is a deflection in the needle. Again note down the position of the needle. So this is 66 and this side again 66. So this is your theta 3, theta 4, right? So it means for one position you will have 4 values of theta. Theta 1, theta 2 is for the direct current. Theta 3, theta 4 is for the reverse current. Now we will move it to 5 cm. You can keep it at any position. Like I will go from here 0, 5, 10, 15, 20, 25 in the steps of 5. So now it is at 5. You can see when I move this, your compass box is moving. So now it is at 5. Again, I will click here to see now as it is away from the coil. So what is the position of needle? Now it is 54, 54. Theta 1, theta 2. Right? Reverse current, Again 54, 54. So theta 3, theta 4. So like this, you will have 4 values of thetas. So here when we are doing, you will almost get the same angle for theta 1, theta 2, theta 3 and theta 4. But when we perform the experiment in your actual lab, so then there is a slight difference in the values. Like here if you are getting 54, maybe on the reverse current you will get 52 or 55. Okay? But here you will get almost same values. Likewise, you will repeat your experiment. Now we will change this position to 10, or you can go for the normal view and see now I will move the compass box to 10 centimeter. Like this. Again click on zoom compass box so that we can clearly see the deflection. So now these values are your theta 1, theta 2. So like this is 29, 29, theta 1, theta 2. Reverse current, this is your theta 3, theta 4. Like this you have to repeat your experiment up to 25. Like, go to the normal view. Then you repeat this for 15. Click on the zoom, note down the deflections. So for each position you will note down the 4 angles. So like this you will go up to 25. Now we will move it to the another side. Now you can see if I take it -5 as it is showing on the slider, it is moving to the opposite side. So again, we'll note down the deflections. So this is 54, 54. So now for x is equal to +5, we already had the 4 angles. Now for the -5, again you will note down the 4 angles, 2 for the direct current and 2 for the reverse current. Like this. Then again, you move it to -10. You can see the deflection in your needle. So this is -10. Note down these angles. Then reverse your current. Again note down these angles. Right? So like this you have to repeat up to 25. So we can also say that we are moving from left side and right side of the coil, or we can also talk about east and west directions. So once you are done, you have taken all the readings for all the position on the both sides.
You will have to write in observation table and prepare a graph as given in the next slides.